Hello, everyone. This is Jianlin from University of Waterloo. This is a joint work with Yizhou. The title of our paper is Compiling with Generating Functions. We present a new approach to scaling exact inference in Bayesian probabilistic programming using probability generating functions as a compilation target. Now, here is an example of a probabilistic program. The function Poisson packet arrival models network traffic, where packets arrive accordingly to a Poisson distribution, which is a standard assumption in traffic modeling. It first samples x from a Poisson distribution with parameter lambda. Then, the loop sum expression uses x as the number of loop iterations, computing the sum of the loop body. The loop body calls forward packet, which returns 1 if a packet reaches the destination and 0 otherwise. We use flip theta as shorthand for sample Bernoulli with parameter theta. This forward packet function models a 2x2 network topology and the probabilistic behavior of the router network, where each link has a 10% chance of failure. So the loop sum expression simulates forwarding all x packets through this network topology and computes the total number of packets that were successfully transmitted. Note that the forward packet function may be arbitrarily complex. Say it could be a 3x3 grid or a n×m grid. Programs like this are challenging for current PPLs. For example, DICE is a state-of-art PPL. It compiles probabilistic programs to binary decision diagrams, BDDs, for exact inference. Jianlin is another state-of-art PPL. It's imperative, and it compiles to generating functions for exact inference. DICE cannot handle the infinite support Poisson distribution and does not support loops. Jianlin supports Poisson distributions, but it struggles to scale to complex networks. And Jianlin does not support loops neither. Sampling-based methods, including importance sampling and Hamiltonian Monte Carlo, they are used in probabilistic programming languages like Pyro and Stan. These methods struggled on this inference problem. The cause is the high-dimensional discrete structure and its non-differentiability. We implement our approach in a probabilistic programming system called Jianlin. Jianlin is a functional PPL. The central component of Jianlin is the compilation from PIL to DIL. PIL, probabilistic intermediate language, is a functional probabilistic programming language, and its only base type is the natural numbers. DIL, deterministic intermediate language, is the target language we use to specify generating functions, where the base type is the real numbers. You can think of DIL as a standard expression language, first order simply typed lambda calculus with real numbers and product types. Jianlin is expressive since it supports finite and infinite support discrete distributions, continuous priors, Bayesian observations, and a restricted form of unbounded loops. Jianlin is scalable since it effectively exploits independence and determinism in program structures, enable compiler optimizations that reduce the dimension of generating functions and derivative computations. Jianlin is accurate since it's doing exact inference. Before we dive into the details of Jianlin, let's first go through the basic ideas of probabilistic generating functions real quick. For random variable x supported on the natural numbers, its probability generating function is defined as the expectation of the formal parameter lowercase x to the power of random variable uppercase x, that is a weighted sum where the weights are probabilities. For example, if x is a Bernoulli random variable with parameter 0.1, the generating function is a polynomial with 2 items where the coefficients are probabilities. Here, the lowercase x, a real number, is the formal parameter, while the uppercase x in the exponent, a natural number, is the random variable. From a generating function, we can recover probability masses and expectation by taking derivatives. For example, the probability of x being 0 and 1 can be computed by taking the 0 order and first order derivative at 0. So far, generating functions may not seem that useful. But in fact, many common infinite support discrete distributions has closed form generating functions. For example, the geometric distribution, the Poisson distribution, and common continuous distributions also have generating functions, such as the exponential distribution and the Gaussian distribution. By choosing generating functions as compilation target, a PPL can represent these distributions, making it more expressive. To represent probabilistic programs as generating functions, the concept of generating functions need to be generalized from the single variable case to the multivariant case. A multivariant generating function serves as a container for all in-scope random variables. When a variable xi goes out of scope, we remove it from the typing context and marginalize it from the generating function by set xi to 1, yielding the generating function of the remaining dimensions. Generating functions also support affine arithmetic expressions, and based on this, we can derive that for two independent random variables x and y, their generating function of their sum is the product of their generating functions. Next, I will show how Jianlin compiles PLL programs to generating functions with simple examples. For arithmetic expressions, for example, a random variable z defined as the sum of x and y, where x and y are sampled from Bernoulli 0.1. The generating function of z is the product of their generating function evaluated at z. At this point, you can verify that the three coefficients are the probability of 0 being 0, 1, and 2. And note that in Jianlin, the representation remained factorized. In Jianlin, we designed and supported a restricted form of unbounded loop. Here, x is a random variable that determines the number of loop iterations. And forward packet denotes a distribution together with its generating function of random variable y. Let that be the random variable representing the sum of x many independent samples of y. By previously shown equation, the generating function of z is gy of z raised to the power of x. But since x itself is a random variable, we need to marginalize it out. So after a few rewrites, the generating function of z simplifies to the composition of the generating function of x and y. Jianlin is the first PPL that is able to express and exactly solve this traffic analysis model thanks to this loop sum construct. Jianlin achieves good scalability thanks to compiler optimizations and the nice properties of generating functions. Let's now see how these techniques work in practice. Jianlin exploits independence and determinism in programs and keep generating functions factorized. Consider this PLL program on the left. It computes Sn as the sum of x1 through xn. The program returns 1 if Sn is greater than 0 and returns 0 otherwise. In other sense, it represents the disjunction of n Bernoulli random variables. We start from the generating function on the first line. It is the trivial generating function for the empty typing context. It takes no arguments. Each line of the PLL program transfers a generating function to another generating function with one additional parameter. In this case, the first line of the PLL program transforms the trivial generating function into a generating function that takes x1 as input. And then the second line of PLL program further transforms it into a generating function, takes x1 and s1 as input. Up to this point, the random variable x2 is independent of x1 and s1. So the new generating function is the product of the previous one and a factor associated with x2. In other words, it remains factorized. Then after a few steps, let's pause before the anything else and look at the generating function closely. It takes 2n parameters as input. It's factorized. It's a product of n factors. Each factor contains on operands, So evaluating this factorized generating function requires O(n squared) time. If Jianlin does not exploit independence and does not keep generating functions factorized, the resulting generating function would expand into exponentially many terms, and evaluating the expanded generating function requires exponential time. Factorization reduces the complexity from exponential to quadratic. This is good, but not good enough. A key optimization in Jianlin compiler is the marginalization of variables when they are no longer alive. Optimizations reduces the input size of intermediate GF expressions created during the compilation, which can lead to saving in time and space during inference. We start from the generating function for the empty context again. But here we realize this line is the last use of x1, which means that we don't need x1 anymore. So we could marginalize x1 out from this generating function by set x1 to 1, yielding the generating function of only one random variable, s1. x2 is still alive here because it's used in the next line. s1 and x2 expires after s2 is defined. So here we could marginalize s1 and x2 out. Importantly, these substitutions are carried out in exec when the variable's liveness ends. After a few steps, let's pause again before the if then else. Now this generating function only takes one argument. Since all dead variables are already being marginalized out, let's look at this generating function closely. With the expired variable marginalized earlier, the generating function at this point takes only one argument and can be evaluated more efficiently in linear time thanks to the factorized structure. By contrast, if the marginalization was delayed until the end of the program, the previously shown generating function would be generated. It takes two arguments as input, and evaluating this generating function requires O(n squared) time. So early marginalization further reduces the complexity from quadratic to linear. I think this is good enough, and this is the best we can do in theory. One of Jennifer's main performance bottleneck is taking derivatives. But by definition, the probability of a variable being non-zero is a sum of derivatives. The sum may be finite or infinite, and evaluating derivatives is computationally hard. While in Jianlin, there's no need for differentiation when testing if a variable is non-zero. We note a perhaps obvious fact for a random variable x supported on the natural numbers. The probability mass of non-zero event can be directly read off from its generating function as follows without differentiation. This optimization seems simple, but it's super effective. It allows Jianlin to avoid differentiation for a large class of programs. Basically, all the programs can be expressed by this. For example, consider the compilation of the if expression in the previous example. There, the generating function GSN is the symbolic representation of the program execution before the if statement. Jianlin transforms it into two GF expressions with constraints GSN to the case where Sn is true and false respectively. The else branch GF is obtained by setting Sn to 0, while the then branch GF is obtained by subtraction. Differentiation is not required here. The final generating function g of z is the sum of transformed generating function from the then branch and the else branch respectively. G of z describes the probability distribution of the program's return state. Here it tells us the probability of returning 0 is the product of theta 1, theta 2, all the way up to theta n. With this background on generating functions and core ideas of Jianlin established, we are now ready to discuss the formalism of our compiler. Our compiler correctness theorem can be viewed as a commuting diagram. PLL, the source language, a functional PPL. DLL is the target language, a deterministic expression language that describes generating functions. The blue arrow from PLL to DLL represents GF compilation. We can view GF compilation as symbolic execution of a PLL program and a PLL program as transformers between generating functions. The orange line from PLL to its denotational semantics. The denotational domain is measure transformers. We use a measure transformer view to define the denotational semantics and the GF transformer view to define the GF compilation. The payoff is a tight correspondence between the denotational semantics and GF compilation. This tight correspondence makes the correctness of the compiler almost self-evident. Since we work in a functional setting, which improves the modularity but complicates the GF compilation and the formalism, we introduce a generalized notion of generating functions. And generalized GF operates on semantic substitutions for typing context rather than fixed size vectors. This black arrow sends measures to generalized generating functions. DLL is mostly a standard expression language, so its denotational semantics is also standard. The compiler's correctness theorem says that GF compilation preserves measure semantics. In other words, this diagram commutes. We evaluated Jianlin on a set of exact inference benchmarks. First one, the grid network. It's from the ProbLog paper computing the probability that a packet from the top left router reaches the bottom right router. We consider two variants, probabilistic link failures and probabilistic router failures. Both plots suggest that the runtime of dice grows exponentially in the square of the grid side lengths, while Jianlin grows exponentially only in the side lengths, demonstrating better scalability than both dice and ProbLog. Let's back to our very first motivating example, Poisson packet arrival. This benchmark exercises two key features of Jianlin: infinite support distributions and the loop sum constructor. Because existing tools for exact inference cannot handle this program, we compare against Pyro's importance sampling. In this plot, we show the L1 distance between the true posterior expectation and the estimated expectation from the importance sampling as time progresses. While Pyro eventually converges, but it only begins to show signs of convergence after 10 minutes. In contrast, Jianlin swiftly produced the exact solution. To our best knowledge, Jianlin is the first system can automatically derive exact solutions for this class of probabilistic programs. DICE has been applied to probabilistic model checking, where it is shown to outperform state-of-the-art model checkers such as Storm on some benchmarks. We also compare DICE and Jianlin on such verification task called weather factory. The task is parameterized by time horizon h and the number of factories n. The left diagram shows how running time scales with time horizon h. DICE exhibit superlinear scaling, while Jianlin shows linear scaling. This means that Jianlin can exploit Markov property, a type of independent structure, better. Ooh. The right diagram shows how the running time scales with the number of factories n, and Jianlin scales beyond the limit of DICE and Storm. The result identifies a promising application of Jianlin. It's potentially beneficial to include Jianlin in the back end of a probabilistic model checking tool. We also compare Jianlin against DICE and Jianfer on single marginal inference task over Bayesian networks. This table shows that Jianlin and DICE are comparable on Bayesian networks such as Haber2 and PIGS, which contains thousands of parameters, but DICE is faster on larger ones. Jianfer times out on all benchmarks. By contrast, Jianlin can compute exact solutions within 5 minutes for all 7 Bayesian networks in this table. Jianlin and DICE have complementary strengths. On some inference tasks that motivated the use of DICE, Jianlin may scale surprisingly well, where DICE scales superlinearly. Jianlin may scale linearly, And in cases where they are both scales exponentially, Jianlin may do so with a smaller base. These problems also involve substantial independence and determinism. But dice may outperform Jianlin on some other inference problems, particularly those ones with large, dense, conditional probability tables. Handling large conditional probability tables well requires extracting the local structure implicitly presented in the tabular representation. And binary decision diagram compilation in dice largely automates this process. We expect future work to investigate the strengths of these inference methods more thoroughly. To conclude, we designed a PPL compiler with an interesting compilation target, namely generating functions. We demonstrated that with appropriate design choices and optimizations, a GF-based PPL can scale surprisingly well on some difficult inference problem. And in addition, this compiler is proven correct and available on GitHub. Thanks.
So we have time for a couple of questions.
The marginalization itself, right? So I was curious, why did you do it on the intermediate representation and not on the original program, right? Like, what was the benefit of waiting until later in the pipeline to do the marginalization? I was just curious if you considered doing it at a different stage or perhaps on the program before you compiled it.
I would say it's the right time of the pipeline because the PIL program, we don't really change the PIL program. And we apply a program analysis on the PIL program. So we know exactly the time where each PIL variable expires. That's why in the compilation target, we kind of like delete it from the memory. So
got it. Cool. All right, thank you.
Thanks.
Hello, Matthias here. We were using, like ages ago at Bloomberg, we were having a little language for describing probabilistic programs, but what we were interested in was payoffs for financial contracts. And so the interesting thing that we did is I can't just answer the question. So basically we used the techniques you had to simplify our programs, but then at the end we ran like a Monte Carlo. Are you also only interested in like precise, like symbolic computations, or also interested in doing it approximately, maybe doing better than the other system for stuff? Just run Monte Carlo, whatever. You only want the precise answers, the exact answer.
So is your question like, is Jianlin only do exact inference?
Or are you also interested in running approximations, but maybe running them better than before?
I didn't really get the question. Is your question like, is Jianlin only deal with exact inference?
Yeah,
the answer is yes. Jianlin is a very, it's a prototype. We only solve this problem in this paper. And in future, we could imagine if there's a syntax structure that controls the inference method applied to sub-expressions, so we can mix different inference methods. Like this part solved by exact solution inference, that part solved by approximate inference. I think that would be an interesting future direction.
Okay. All right. Thank you. We should probably wrap up and thank the speaker again, please.